Okay, so in the last lecture we applied the mole balance for a PFR. In this lecture we will apply the mole balance to a PBR. And really the PFR and the PBR are very similar. The only difference between them is that in the PBR we take into account the fact that there are catalyst pellets in the reactor. If this is a gas phase reaction, the catalyst pellets can cause drag, which can influence the pressure within the reactor. And since pressure influences concentration, the catalyst pellets can influence the concentration and hence the reaction rate and thus the reactor design. So we will see how all of that comes to play in this lecture. So let's start by doing a review. So let's review PFRs by doing an example. So we have an example, A plus 1/2 B goes to C, and we'll say it's carried out isothermically and isobarically in a PFR, and we want to determine the volume needed for 60% conversion. The feed is stoichiometric in A and B, so we could pick either one of these as our basis for calculation. Let's pick A just because that's just kind of what we normally do. And we're given additionally this information. So the first step always in a reactor design problem is to write down the mole balance. So for PFRs, we have two choices we can make for the mole balance. And which one should we choose? So I'm going to choose the one in terms of conversion, and that's because the problem statement directly asks me about a conversion that I need to achieve. So the PFR mole balance in terms of conversion is FA naught dXA dV is equal to minus RA. The next step then is to fill in this rate law. We have an expression for the rate law here, so that's somewhat simple. We can just write that down. RA is equal to K PA to the 1/3 times PB to the 2/3. And so now I have, if I were to insert this expression into here, I would have a convolution of variables. I'd have P variables and X variables. So I need to get those all in the same terms. So I'm going to write my pressure terms in terms of conversion. So I can use equation 427 from Fogler. And that equation says that the partial pressure of species J is equal to the partial pressure of species A, or of the limiting reactant initially, times theta J plus the stoichiometric coefficient of species J times XA divided by 1 plus epsilon x. So I need to write a pressure expression for A and B. So we're going to say that the pressure of A is equal to PA naught 1 minus XA divided by 1 plus epsilon XA. And for the partial pressure of B, we're going to do something similar. PA naught is equal to theta B minus 1/2. So the stoichiometric coefficient on B is 1/2, and since it's a reactant, we're going to convert it to a negative 1/2 for this equation, times XA divided by 1 plus epsilon XA. Now, if I were to fully write out this equation, I would have two additional terms here. I would have a P divided by P naught term, and I would have a T naught divided by T term. But since this is an isothermal and isobaric reaction, those terms both are equal to 1 in this example, so I'm going to neglect them. But keep your eyes out, that's not going to be the case later in this lecture. So now the only thing I have left to do, I have to solve for, or I have to provide a value for theta B and also one for epsilon. Let's do theta B first. So theta B is equal to FB naught divided by FA naught. The problem statement says that A and B are fed in stoichiometric proportions. That means that FB naught, the stoichiometric ratio of B to A, is 1/2, so that means that theta B is going to be equal to 1/2. So I could substitute this into here. I'm just going to leave it as is. The next step is to get delta and epsilon. So delta, recall, is the number of, or the change in the number of moles across a reactant per mole of limiting reactant. So if I go back up to my reaction, the stoichiometric coefficient on A is 1, so I don't need to do any normalization here. Basically, I have 1.5 moles on the product, or on the reactant side, and 1 mole on the product side. Therefore, I have a change of negative 1/2 moles. So delta is equal to minus 1/2. Epsilon is equal to YA naught times delta. So now I need YA naught. So YA naught is the initial mole fraction of species A. So the number of moles of A fed divided by the total number of moles. In my stoichiometric ratio, I'd have 1 mole A divided by 1 mole A plus 1/2 mole B. So my inlet mole fraction of A is going to be equal to 2/3. Therefore, epsilon is going to be equal to minus 1/3. So I now have enough information to solve this problem. I basically take my pressures, or my expressions for my partial pressures, and I insert them into the mole balance. And I could separate variables and integrate and solve. And doing that, my limits of integration, x is going to go from 0 to 0.6, and v goes from 0 to v. And if I do all of this, I can solve, and I get a solution of v is equal to, you should go through the procedure of performing this solution and see if you can get the same thing. Okay, so now let's talk about PBRs. So to do that, first let's compare and contrast the PFR and the PBR. So similarities. So what are some similarities and some differences between PFRs and PBRs? So some similarities. So they're both tubular reactors. So a tubular reactor, we've said how those operate. The reaction proceeds down the length or volume of the reactor. The flow through the reactor is plug flow. By plug flow, we mean turbulent flow. There are laminar flow tubular reactors. We're not going to study them in this class, but if you were to take graduate chemical reactor design, you might encounter them there. So other similarities are perfect mixing in the radial dimension. And then we have a continuous variation down the length of the reactor in the axial dimension. When I say continuous variation, I mean in the reaction properties, such as the concentration and the temperature. We'll say down the length. So pretty much these two reactors operate very similarly. The difference is that the PBR is packed with catalyst pellets. So PBR So when we think about how the PFR is operating, that's basically like the transport problem flow through a packed bed. So the fluid goes down the reactor, and as it's doing so, it's flowing by a bunch of packing. And because of this, so gases in the PBR may experience pressure drop due to the packing. That's really the only difference between the PBR and the PFR, at least as we'll encounter them in this class. Sometimes for a PBR, you're given different units for the problem. For example, we're going to write the mole balance as in terms of the catalyst weight, or actually it's catalyst mass, but we denote it as W, instead of in terms of the volume as we do for the PFR. But in reality, the catalyst mass and the volume of the reactor are related. We can always write a catalyst density in units of mass per volume. So we can always make that conversion. So that's mainly a matter of convenience, and we don't even have to do that. You will see mole balance problems for PBRs that are written in terms of volume. In those cases, someone has already gone through and done the conversion between mass and volume. Okay, so what is meant by packed bed? So the PBR, packed bed reactor, not to be confused with Pabst Blue Ribbon. So if I draw my reactor, my tubular reactor, so I'm going to draw this in a similar way as we've been doing in this class. So I have a tube, or a pipe, and if this is a packed bed reactor, then we would say this would be filled with catalyst pellets. So this is not straightforward to draw with this digital drawing tablet, so I will just do my best. But basically, and you can imagine this is looking rather ordered, it would not be so ordered. You'd have some packing, a bunch of spheres. And this I've drawn these here, but this would be throughout the reactor. You'd have this these spherical packing. And so if I zoom in here, so zoom in, so I'm going to zoom in on one catalyst pellet, and what you would see is the gas would approach the pellet, and then it would flow past the pellet. So you have flow past a sphere. So you probably saw problems such as this in your fluids class. So we're going to call this flow around a spherical particle. So in reality, there are a variety of different shapes that the catalyst pellets can assume. In this class, it's perfectly acceptable to think about them as spheres. If you were to get into graduate reactor design, you might look at different shapes. In this class, the spherical model is perfectly good for thinking about what this packing looks like. So we have this scenario. We have a packed bed. This causes, when we have a gas, the gas has to flow around these particles. And the implication of this, the flow around the particle, this causes drag. So in other words, there's a opposing force on the gas due to flowing past this particle. The drag causes pressure drop. So pressure drop means a decrease in the gas pressure. The decreased pressure causes a decrease in concentration. The decreased concentration influences the rate. We'll say the rate law. So hence, it has a significant influence on the design of reactors involving packing. catalyst packing. So we need to account for this pressure drop. So we account for it using the Ergun equation. So if you recall from your fluids class, the Ergun equation takes this form. So the change in pressure down reactor length is equal to this expression. In this equation, we want to look at this bracketed term right here. This part dominates in laminar flow. And this part in turbulent flow. So you can look up what all of these variables stand for. The terms that we're going to concern ourselves with right now, capital P, so this is capital P. That is the total pressure. Z, in the bottom here, is the reactor length. So that's going to be equal to the reactor volume divided by the cross-sectional area. And then dP, so if we go back here, dP is the diameter of the catalyst pellet. So it's a catalyst pellet diameter. So one thing you can see is that the smaller the catalyst pellet, the larger the dP/dZ term. So the catalyst, if you have a smaller catalyst pellet, it's going to have a larger influence on the pressure drop. So this is the full expression for the Ergun equation. In this class, we're going to simplify it. So rather than spend a lot of time parameterizing the Ergun equation, we just want one parameter that's basically going to give us an idea of how much the pressure is going to drop for a particular equation. So we use simplified forms, and so those are given in Fogler. The general equation is dP, and this is lowercase p, dW, so in terms of catalyst weight, is equal to minus alpha, that's our parameter, divided by 2p, lowercase, T naught over T, Ft over Ft naught, or in terms of x, so this is in terms of flow, F terms, now and we can write in terms of x, dP, lowercase p, dW, minus alpha over 2p, T over T naught, 1 plus epsilon x, and here, these two, I did this incorrectly. It should be T over T naught, just like it is over here. So let me see if I can fix this quickly. So those are my simplified Ergun equations. In this case, we have decreased all parameters down to this, or we've collapsed all parameters into this one single parameter alpha. This value will, for the most part, be given to you in this class. So the important terms in these equations, lowercase p is equal to P divided by P naught, where P is the total pressure at any given point. We'll say at some location. within the reactor. So some point down the length or volume, and then P naught is the total pressure at the reactor inlet. So different than in the last case. In the last case, we were looking at the drop in the total pressure. In this case, we've reduced that into the change in the pressure relative to the inlet pressure. So lowercase p here versus uppercase above. And also here we have alpha. This is the Greek letter alpha, and it's the pressure drop parameter. And it has units of inverse mass. This makes sense. So if we look at this equation, the top term here, the lowercase p, that's unitless because it's pressure divided by pressure. The denominator has units of mass. And then if we look at all of the terms on this side, everything is unitless except for alpha. So henceforth, alpha has to have units of inverse mass. We could make the argument that alpha is related to dp, and this is what we were talking about earlier, the relationships between alpha and dp. So we want to say as dp increases, alpha decreases. So the larger the particle, the less pressure drop. And by contrast, as dp decreases, alpha increases. So smaller catalyst pellets give rise to larger pressure drop. So let's actually write that down. Smaller catalyst pellets, more pressure drop. So that said, if you think about a spherical catalyst pellet, and let's actually go back up and look at, so if this is a spherical catalyst pellet, and we'll get into this more when we study catalysis, but usually the catalytic activity would not be happening on the surface of this pellet. This pellet is going to be a porous material, so lots and lots of pores here inside the pellet. So think about a sponge and how it has pores and how fluid can travel into the pores in the sponge. Now, a catalyst is not identical to a sponge, but at least for illustrative purposes, the porosity kind of works the same way. So the surface area inside this catalyst pellet is actually really large because of all the pores. So there's probably, hundreds of meters squared of surface area per gram of catalyst pellet. So that's why a lot of the most of the activity is going on inside the pore, because you got a lot more surface area there. So what that says is for the catalyst to be active, gases are actually going to have to diffuse into this catalyst pellet so that they can contact the catalyst material there and react. And we'll get into that later in the class, so you don't have to worry too much about that right now. But you can imagine what the implications are in terms of catalyst size. So if you have a very small catalyst pellet, then it's going to be a lot easier for particles to diffuse into that catalyst pellet. But if you have a large catalyst pellet, then the path that the molecules have to take in diffusion is much larger. So there's a relationship here, there's an optimum. When you think about a catalyst pellet, you want to have a large enough catalyst pellet such that your pressure drop isn't significant, but you want to have a small enough catalyst pellet such that diffusion isn't inhibiting your reaction. So we'll get into this later in the class. But for now, let's say smaller catalyst pellets mean more pressure drop. However, larger catalyst pellets mean larger paths for diffusion of molecules inside the catalyst. inside the catalyst pores, and this can impede the reaction rate. And we'll get into that more later in the class. Okay, so that is the Ergun equation. So how is this applied? So the Ergun equation, it couples with the mole balance. So now you're solving a coupled set of ordinary differential equations when you're solving the PBR or reactor design equation. So solving this set of coupled ODEs usually requires a numerical solution using software. So in the very next lecture, I'm going to show you how to do that using Python. There's one exception when epsilon equals to 0 and t divided by t naught equals to 1 that has an analytical solution. And I believe you're going to work with a problem involving that scenario. Okay, so last things for this lecture. Let's apply this, let's practice with it. So let's take the exact same example that we did at the beginning of the lecture. This time we'll assume the reactor is a PBR with pressure drop, so it's no longer isobaric. The only other changes I'm making are I'm changing the units of this rate constant so that we can write our mole balance in terms of dW. And also we're giving you a pressure drop parameter alpha equal to 0.0367 inverse kilograms. So let's solve this. So the mole balance for the PBR looks just like the mole balance for the PFR, Fa naught dx dW equals minus Ra, except in this case, instead of having a dV term, we have dW. So again, instead of solving for the reactor volume, we're going to solve for the catalyst weight, but these two terms are related by a simple scalar conversion factor. Okay, so the rate law here is the same. It's going to be this K times PA to the 1/3 times PB to the 2/3. And then you'll see if we multiply this by our rate constant, the units set us up well for that. We have atmospheres here on the bottom. The pressure terms have overall units of 1 atmosphere, so this part is going to cancel out. And then our rate is going to be in units of moles per kilogram catalyst per time, which is exactly what we want. That's our rate, going to be the units on our rate, and that's going to match with the units on this side of the equation. Other things that are different, there's at least 2 big ones. What are they? One is, of course, the Ergun equation. So one, need to include Ergun equation. So the Ergun equation, the form of that I'm going to use is the one in terms of conversion. So we're given 2 forms of the Ergun equation, one in F terms and one in X terms. Since I've written my mole balance in X terms, I'm going to also write the Ergun equation in X terms. And again, that's because I cannot convolute the variables. If I had chosen instead the F, the flow version of the mole balance, I would choose the flow version of the Ergun equation. So whichever form I choose of one, I have to be consistent and choose the same form for the other. In that case, that's this equation. So the Ergun equation, dP dW is equal to minus alpha divided by 2p 1 minus 1/3 x. The limits of integration here, so P goes from what two values? Let's start out at. So P, lowercase p, is equal to the total pressure at some point within the reactor divided by the total pressure initially. So it starts out as 1 to some value P. We don't know what it's going to end up at. And W from 0 to W. What's my other big difference here? It's a little more subtle. It's going to be in the way I write my partial pressures. So expressions so this equation (4-27). So where I'm writing the change in the partial pressure down the reactor, and it's the partial pressure is changing both due to conversion, so reaction, but also due to the change in volumetric flow rate down the reactor for this particular problem. Then this would be true. I'm writing in terms of partial pressure, but this would be true if I was writing in terms of concentration also. So basically, now that I have a pressure drop term, I have a non-isobaric reaction. I have to account for that. So that is going to influence my volumetric flow rate also. So I have my PA equation goes to PA naught 1 minus x divided by 1 minus 1/3 x. And now I have this lowercase p term here. And again, this is a partial pressure term, but if I had used equation 4-25, which is for concentration, I would still have this term here. So a big mistake that students make is forgetting to include this. If you don't include this, then you're not going to have the effective pressure drop on your rate expression, because your partial pressure or your concentration is not going to be dependent on the pressure drop. So your solution will end up being identical to the PFR solution. So if you want or actually need to account for pressure drop on your solution, then you need to remember to include this term in your expressions for your pressure or concentration. And so I could do the same thing for PB, 1/2 PA naught 1 minus XA divided by 1 minus 1/3 x times lowercase p. And so we'll say this is lowercase p and it takes into account the effect of pressure drop on volumetric flow rate. And you will see, so all of these equations that we've listed that account for changes in volumetric flow rate, this pressure term is included in all of them. So you need to include this term if you have pressure drop, even if you don't have a change in moles accounting for a change in volumetric flow rate. So if you have pressure drop, this is a separate effect than the change in volumetric flow rate due to the number of, or due to a change in the number of moles. So review these formulas. It's like 416, 417, 423, 425, and 427 in Fogler, and see how this term enters in. This is now the key point that we need to start including this when we have pressure drop. So we'll say key point pressure drop influences volumetric flow rate and hence concentration. And this is true even in cases where the number of moles does not change. So it's a separate effect. So that's all I want to say here. In the next lecture, we'll actually go through and enter these equations into Python and solve this problem involving these coupled ODEs.